Okay, so this is Chapter 4, Lesson 4. Okay, so this is Chapter 4, Lesson 2, and today we're going to talk about electrolytes, and then we're going to talk about precipitation reactions and solubility rules. So let's talk about the difference between electrolyte and a non-electrolyte. So in the past you've heard me say that electrolytes are the substances that have the ability to conduct electricity. And why do they have that ability? Well, it's because they form ions in solution. So substances that form ions in an aqueous solution. And the popular example is NaCl, which is simply table salt. Whereas non-electrolytes don't. And a good example of this, it would be a sugar like C12H22O11. So what is the difference between strong and weak electrolytes? Well, strong almost completely dissociate in water. And we say that's about like 99 to 100%. So a good example, sticking with NaCl, would be NaCl solid dissociates into Na plus and Cl minus. And this is AQ, both of these. Weak only slightly dissociate. So for example, acetic acid, which is simply vinegar, basically stays as acetic acid. There's only a slight dissociation. Oops. Okay, so an example of this, is this diagram right here. So here you have solubility, meaning dissociation, high versus low. You can see where the molecules completely separate, and here they're still clumped together. So we're going to have varying differences in electrical conductivity. Now, just because something is soluble does not mean that it is a good electrolyte, and vice versa. Just because something is a weak electrolyte doesn't mean that it's insoluble. Most ionic compounds are strong electrolytes. Okay, so This diagram, and I've done this demonstration in Regents Chem, you can see the difference in electrolytic properties. So in this first one, there's no ions whatsoever. So this is like me dissolving sugar in water. So this is a non-electrolytic solution, and the bulb won't light because we need the ions to complete the circuit. In the middle one, we have a few ions. So if the solution contains a small number of ions, the bulb will be only dimly lit. So this is what we would call a weak electrolyte. And in the last one, we have many ions. Therefore, the bulb will light very brightly. So this is what we call a strong electrolyte, and these are usually our ionic compounds. Our weak electrolytes are some of our acids and bases, because some of our acids and bases are also considered strong, so we'll look at what that list is also. So let's look at strong versus weak electrolytes in equilibrium. And what are we talking about there? Remember that some reactions go to a completion. So when you see a reaction that has a single arrow, it usually means that it goes to completion. So an example of this would be a strong electrolyte such as nitric acid. This is going to completely dissociate into solution into its respective ions of H plus and NO3 minus. Now some reactions will have a double arrow, which means that there's an equilibrium balance between the forward and the reverse reaction. And this is the case with the acetic acid that I showed you. So although it does dissociate, and then sometimes I wrote two half arrows, sometimes it's simply written like this, okay, or two half arrows. There's an equilibrium balance between what dissociated and what didn't. So the extent of dissolution does not indicate whether something is actually strong or weak. So here you have acetic acid, which is very soluble, it's vinegar, but weak, whereas we might have barium hydroxide, which is only slightly soluble, but it's a really strong electrolyte. And that's what I was trying to say in that first slide. Now, we can also think of this equilibrium like a tug-of-war. So here you have your forward and your reverse reaction, and it's going back and forth until they actually reach a middle ground. Alright, and here is an example of what I was talking about. Here you have a strong acid, okay, and you can see that it completely dissociates. And here you have a weak acid, and they're using just the A minus and the B minus as a generic anion. And you can see in this one over here that less than 99% stayed, or less than 99% only dissociated. So like 1% dissociated, and the rest stayed intact. Okay, so let's talk about precipitation reactions. First of all, whenever you see a precipitate, that's going to be abbreviated PPT, precipitate. And a precipitation reaction is simply when a precipitate forms. And the solubility rules that go with precipitation reactions allow us to make predictions about the precipitate. So to define precipitation reaction, which you already know what it is the formation of an insoluble solid. And that means less than 0.01 moles per liter. An example of this would be AgNO3 aqueous plus NaCl aqueous, so silver nitrate and sodium chloride. And if I mix them in a test tube, I'm going to get a white precipitate, which is the formation of the silver chloride. And the clear liquid above it will be sodium nitrate. Now, how do we know what's going to form a precipitate or not? Well, there's something called no-so. Let me explain to you what that is. I actually put up on our page Quizlet flashcards for you to study because you need to know your solubility rules, and we will have a quiz on that sometime next week. So we have what's called no-so and hydroxides. So let me explain a little bit about what this means. So the Na in the NOCL, the Na is group 1. And all group 1 are all soluble, no exceptions. So that means anytime Na is in a compound or any other group 1 element, it's going to be soluble. The Cl comes from group 17, or the halogens, and they are all soluble except when combined with mercury, lead, or silver. The No stands for nitrates, acetates, and chlorates. And they are all soluble. The So stands for sulfates. And they are all soluble except barium, calcium, lead, and mercury. Barium, calcium, lead, and mercury. And it's easy to remember those because they're all 2+. And then the last one is and hydroxide. So OH minus, hydroxides, right? They are all insoluble except calcium, barium, and strontium. So what that means is all my hydroxides are basically insoluble unless it's calcium hydroxide, barium hydroxide, or strontium hydroxide. But then you might say, Miss Nielsen, well, what about sodium hydroxide? Well, sodium falls under the group 1 rule, the Knockel rule, all soluble, no exceptions. See how that works? Okay, so let's take a look at this other slide here. Okay, so here's what's going on, a precipitation reaction. Here you've got potassium iodide, it's a colorless solution, and lead nitrate. I mix the two of them together and I get a bright yellow precipitate, lead iodide. So let's talk about that. Ki, potassium iodide. It's going to be soluble. Why? According to Knockel knows so, K is a group 1 element, so it falls under the Na rule. Not to mention that iodine is group 17, falls under the Col rule, and there's no mercury, lead, or silver. In the second one, you have lead nitrate. Lead nitrate is going to be soluble under the No rule, nitrates. Remember, Knockel knows so. So under the No rule, nitrates are all soluble, no exception. So my two reactants are soluble. But when I mix them together, lead iodide falls under the Col rule. Halogens, group 17, are all soluble except for when mixed with mercury, lead, or silver. And here we mixed it with lead, so it's going to form a precipitate. KNO3 falls under the No rule again, the nitrates. It's always going to be soluble. There's no exceptions. Okay, and this is a slide like right out of the textbook. This talks about the nitrates and the group 1s. However, there's no order to it. The Knockel knows so acronym was put together to help students and instructors like myself have an easier time memorizing the solubility rules. So let's take a look at these examples right here. Using your solubility guidelines, predict whether each of the following are soluble or insoluble. So I have AgI. Right away, I know that I comes from Col. Okay, halogens are soluble except for when combined with silver, lead, or mercury. So this is going to be insoluble. Na2CO3, sodium carbonate. That forms under the Na rule. Okay, all group 1 elements are soluble, no exceptions. Barium chloride. Okay, we have no rule about group 2, but we have a rule about chlorine. The Cols fall under the halogen rule. Soluble unless combined with silver, lead, or mercury. Silver, lead, or mercury. So this is going to be soluble. AlOH3, all hydroxides are soluble except for calcium, barium, and strontium. So this is going to be insoluble. And zinc acetate. Acetate falls under the No rule. No is nitrates, acetates, and chlorates. All soluble, no exceptions. Okay. So let's talk about metathesis reactions. Metathesis reactions. Metathesis reaction is simply a double replacement reaction. We got two compounds and they're going to switch partners. That's what ion exchange means. It's usually in the format AX/BY yields AY/BX. Now, Remember at the beginning of the year, I told you to memorize your polyatomic ions, made you take a quiz on them, and here's the reason why. Because now we're going to be doing heavy reaction writing. We don't have time to look up those ions. Got to just be able to right off the top of your head. So, what is special about metathesis reactions? These reactions are driven to completion by the removal of ions from solution. Well, how do we remove ions from solution? First way is the formation of a precipitate. That's what we've been talking about. The second way is the formation of a gas. Because if we form a gas, it usually vaporizes and leaves the solution. And the third way is the formation of a weak, soluble electrolyte or non-electrolyte and this could be a couple of things, but usually it is the formation of water in a reaction. So let's look at an example. Okay. So this is driving force 1, formation of a precipitate. Predict the precipitate that forms when aqueous solutions of barium chloride. Here you go, you need to be able to write it. Ba, it's got a +2 charge, Cl2 when I drop and cross, and potassium sulfate. K, sulfate is SO4 with a 2- charge, so when I drop and cross I get K2SO4. That's how it's got to come. You got to be able to do that right off the top of your head or you're going to get waylaid there. Now they're going to switch partners. Ba is going to hook up with the SO4. It's +2 -2, so it's a 1-to-1 ratio. And the K is going to hook up with the Cl, so that's a +1 -1. It's a 1-to-1 ratio. We said that these were aqueous solutions, so we should have AQ written here. And now I have to look at my products. When we go back to our rules, NOCL, no SO. So, what falls under SO? Sulfates. Sulfates are all soluble, except when it combines with barium, calcium, lead, and mercury. And there's your barium, so this is going to be your precipitate or your solid. And according to the Cull rule, KCl is soluble because the only 3 exceptions to the halogens are silver, lead, and mercury. And they want us to balance this, so we got 2 Ks, so we need 2 there, 2 Cls, we're good. Everything else is balanced. Okay, so let's look at another driving force, the formation of a non-electrolyte or weak electrolyte. Examples often are acid-base reactions that fall into this type. We're missing an arrow here on the PowerPoint. So we have HCl and sodium acetate, and they're going to combine and form NaCl and acetic acid. So acetic acid is a very weak electrolyte. As I already told you, it's vinegar. In the bottom one, we've got a strong acid and a strong base combined to form salt and water. So here's your formation of water. And our last driving force is the formation of a gas that is insoluble in water. And two of the most popular gases that usually form in these type of reactions are hydrogen sulfide and carbon dioxide. So here we have HCl and sodium hydrogen carbonate, and you're going to form sodium chloride solid and carbonic acid. And in the second one you have carbonic acid that's going to break down and form water and carbon dioxide. And yes, this is currently from the stoichiometry lab that you're doing. Okay, that's it. Please check out the problem set, and I will see you in class.